Hello everyone, this is SAVITHA Acharya from Canara Engineering College. In this lecture video, we will begin with Module 3, that is Gate Level Modeling. In Gate Level Modeling, we describe the digital circuits using basic gates. Verilog supports basic logic gates as predefined primitives. These primitives are instantiated like modules except that they are predefined in Verilog and do not need a module definition. What I mean is, for example, we can realize a full adder using two half adders. But half adder is user defined and hence the user need to describe this half adder as a separate module wherein you have a module definition and in the body of the module you describe the functionality of the half adder. The difference with the primitive gates is the primitive gates functionality is already predefined in Verilog and hence the user needs to only instantiate these like any module instantiation. You must be familiar with instantiating the design block in the stimulus block while writing the test bench. All logic circuits can be designed by using basic gates. There are two classes of basic gates, that is AND OR gates and buff NOT gates. We'll deal with the AND OR gates first. The AND OR gates have one scalar output and multiple scalar inputs. The first terminal in the list of gate terminals is an output and other terminals are inputs. That is, whenever you are instantiating these primitive gates in Verilog program, the first terminal in the list of terminals should be the output and followed by the input terminals. So what I mean is, if you are considering a 2 input gate, the first terminal should be the output followed by 2 input terminals. If you are considering a 3 input gate, then the first terminal will be the output followed by 3 input terminals. Accordingly, for n input gate, the first terminal in the instantiation line should be the output followed by n input terminals. So here I have considered the example of 2 input gates, 2 input AND gate and 2 input OR gate. Now we'll be proceeding to write the truth table of this gate. Now you must be thinking what is so different in writing the truth table, because you have been doing this right from the 3rd semester in your digital system design course. But here we'll be dealing more in detail. If you recall, how do we do the module definition? We write module keyword followed by name of the module and inside the brackets we write the port list. Okay, and the next line we start with the declaring the ports, that is depending on the direction whether it is input or output. Now once you declare any port as input or output, Verilog by default takes it as the default data type. The default data type in Verilog supports 4 values, that is 0, 1, X and Z. 0 and 1 are the binary bits and X is unknown and Z is high impedance. Okay, this is very much important when you are modeling digital circuits in practical digital circuits. Okay, so now instead of 2 binary values in your truth table, it will be considering 4 values. So the truth table will be for AND gate, when input, so let me take this as I1 and I2 are the inputs. Let me take this as I1 and this as I2. So I1 takes 0, 1, X and Z, I2 takes 0, 1, X and Z. So instead of initially you used to have 4 possible combinations with the 2 input gates, now you will have 16 possible combinations. That's why these 16 cells are for these 16 combination outputs. Okay, so here we'll be writing the output for the AND function. So first for the AND gate always there is one, for any gate there is the one controlling input. So for the AND gate 0 is the controlling input, meaning if any one of the input is 0, what is the output of the AND gate? It is 0 irrespective of what the other input takes. Okay, what the other input value is. So if any one of the input is 0, you can blindly write that the output is 0. So this row has got one of the input as 0, so I can simply write output as 0. Likewise, this column also, one of the input is 0 and the other input takes other 4 different values, still the output will be 0. Next, when input is 1 and 1, the AND function is 1. 1 and x. Now x is unknown. When you AND it with 1, we don't know. X could be 0 or 1. So x is so the output is x. Similarly for z, 1 and z, the output is again unknown. We cannot predict. So x and 1 is x, x and x is x, x and z is x. Similarly high impedance. So 1 and z is x, this is x, and this is also unknown x. So these values are resolved based on the strength levels. You must have studied the in Verilog there are 9 strength levels that variable data type can take. Okay, so when there are they are again arranged in weak. Some signals strengths are weak and some are strong in comparison. So when a strong signal is ANDed with the weak signal, then the weak one is overridden by the strong signal. So based on these the signal values are resolved. Next, moving on to the OR gate. So here for OR gate the controlling input is 1. Okay, if any one of the input is 1 for OR gate, the other, irrespective of the other input, the output will be 1. Okay, so based on this theory I can write this column will be 1 because one of the input is 1. So let me take again, this is I1 and this is I2. One of the input is 1, so this entire column will be 1. Similarly, when I1 is 1, also the output will be 1 irrespective of the value of the other input. 0 or 0 is 0 and 0 or x is x, 0 or z is x, x or 0 is x, this is x, x, and z or 0 is x. So if you recall the strength levels, high impedance is the weakest signal. Okay. For the NAND gate, now what is the control input? For the NAND gate, if any one of the input is 0, okay, the output is 1. So for AND gate, if any one of the input is 0, the output is 0. So here NAND is complement of that. So if any one of the input is 0, output is 1. So I can write this column as 1 and this row as 1. Now 1 NAND 1 is 0, 1 NAND x is x, 1 NAND z is x, x NAND 1 is x, x NAND x is x, x NAND z is x, z NAND 1 is x, z NAND x is x, and z NAND z is also unknown. For the NOR gate, if any one of the input is 1, output is 0. So it is simply complement of OR gate. So here also the control input is 1, but the output will be 0 if one of the input is 1. Okay. Similarly, based on the same argument, this row also will be 0. 0 nor 0. 0 or 0 is 0. So 0 nor 0 is 1. Now, whenever one of the input is x or z, the output will be unknown. So it is all these cells are unknown, so it is X. So this is the truth table for the 2 input NOR gate. There is no controlling input as such for the XOR gate. So let me take this input as I1 and this input as I2. 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1 and 1 XOR 1 is 0. And whenever there is one of the input is X or Z, the output will be unknown, so the remaining cells is unknown. Coming to the XNOR gate, again similar to XOR gate, there is no controlling input for XNOR gate as well. So 0 XNOR 0 is 1, 0 XNOR 1 is 0, 1 XNOR 0 is 0 and 1 XNOR 1 is 1. This is simply complement of the XOR gate, and the remaining cells will be X. Okay, X XNOR 0 is 0, X XNOR 1 is 0, X XNOR X is X, sorry, X XNOR 0 is X, X XNOR 1 is X, and so on. The instantiation of AND or gates is similar to any component instantiation or module instantiation that you have seen before. So for your reference, I have repeated the logic diagram of all the primitive gates that is available in Verilog. Now we'll go for the instantiation of these gates. So this is the comment line, that is with the double slash. Whatever follows the double slash is treated as a comment. Now first I will instantiate the AND gate. So the AND gate primitive is AND, the name is AND, and followed by some instance label. Now inside the brackets you have to instantiate the port list. So always the first terminal is the output, and for the second the remaining terminals are the inputs, list of inputs. Similarly, the second gate is OR gate. So the name of the OR gate is OR. Okay. O1 I have given as the instance label. Again, the first one is the output followed by the two inputs. So like this I have instantiated all the gates listed here. That is NAND, I have given some instance label as NA1, out I1, I2. Similarly NOR, I have given instance label as NO1, XOR and XNOR. Now if you have gates with the more than two inputs, that is instantiation of 3 input gate. So in that case, suppose let me take the example of a NAND gate. So the name is NAND again. So whether it is 2 input gate or 3 input gate or n input gate, the primitive gate name is same. Okay. So if we are instantiating a NAND gate, I will the name is NAND. I will give some instance label as N1. So in that case, whatever names you have given in your circuit for your terminals, let me take the same names out and say I1, I2, I3. So like this you can extend the same thing for any number of gates. Also, one more privilege here is only for primitive gate instantiation, you need not give the instance label, that is instantiation without instance label. So I can instantiate a gate, say I can instantiate a gate without giving instance label. Always the syntax is first the name of the module to be instantiated followed by instance label. For primitive gates you can skip this and simply give the terminal list. This is a valid Verilog statement. Now this privilege is only for primitive gates, not when you are instantiating a user defined module. The next category of gates is buff not gates. The buff not gates have one scalar input and one or more scalar outputs. So buffer is the one which transmits whatever is at the input, and NOT gate is the inverter. Whatever is at the input is inverted and given to the output. So what I mean by saying that buff NOT gates have one scalar input and one or more scalar outputs. So here when you have a buffer like this, say one input, and I have a buffer, I can have multiple outputs. Okay, multiple outputs, and this could be driving different signals. These multiple outputs from the same buffer could be driving different sources. Okay, here for example I have taken only one input one output gates. So for a buffer, if we move on to write the values, so input can take 0, 1, x and z. So buffer output also will be 0, 1. When input is unknown, output is unknown, and when input is high impedance, output is also high impedance. Moving on to the NOT gate, when input takes 0, 1, x and z, the inverter output will be 1 and 0. When input is x, output is x, and when input is z, also output is x. As we have learnt earlier, the buffer and the NOT gates are multiple output and single input gates. So first we will look into the instantiation of single input single output gates as shown in these two figures. So the module name or the primitive gate name for buffer is BUF, followed by the instance label. Let me take it as B1. Now first the list of output. So here it's only single output. So out and followed by the input. Similarly, the NOT gate primitive name is NOT. Let me take B1 N1 as the instance label, out, comma, in. Here I have a buffer with more than one output, that is 3 outputs, output 1, out 2 and out 3, and input is in. So again the name of the module or the primitive gate is again buff. And let me take some name B2 instance label. Now here it will be out 1, out 2, out 3. These are the three outputs followed by the input, that is in. So here out 1, out 2, out 3 are the same outputs. I mean the same value is output on different lines which could be fed to different for driving different sources. Okay. Just like we have seen in instantiation of AND OR gates, here also these instances can be instantiated without giving any instance label. That is, say I can take NOT, out, comma, in without any instance label. Again I repeat, this privilege is only for the primitive gates and not for the user defined gates. There is one more type of gates in the second category, that is buff not gates, that is buff if and not if gates. So the difference between the buff if and the not if gates is the buff if and not if gates have an additional control signal called as the control, CTRL, that is what is named here. Okay, so these gates propagate only if their control signal is asserted. Okay, in some cases there are multiple drivers, so we want to drive the signal based on the control signal, that is only if the control signal is active it will drive the signal. So if the control signal is inactive, then they propagate Z or high impedance to the output. So based on this we can write the truth table of this. That is, so here so here let me take this as the input and this is the control input. Okay, and the remaining cells will be the output. These are the input values and these are the control values. So buff if 1 means it will for this the active value of the control is 1. So whenever control is 1, whatever is at the input will be transmitted to the output. So control is 1 here, so input 0 will be transmitted to output 1 X, and input when it is high impedance it will be Z. So when control is 0, that is inactive state of control, the output will be in high impedance state, that is Z. Okay. Now when input control is X or Z, okay, we don't know whether the controls signal, the X means it could be 0 or it could be 1. Okay, so depending on that, the input 0 could be transmitted as a weak low. Okay, and the input 1 would be transmitted as a weak high. L stands for weak low and H stands for weak high. Okay, and for when input is X, it is X, when input is Z, it is X. Similarly for buff if 0, buff if 0 means there is a bubble here, that means whenever the input control is 0, the output will be giving you the inverted value of the input. Okay, so when in control is 0, the output, this is a buffer, so it will be transmitting whatever is at the input will be transmitted for control value 0. When control value is 1, this is the inactive state of the control signal, the output will be high impedance. Okay, and again when X and Z are the values of the control signal, we don't know what will be the value of X or Z. So it will be transmitting, again for a low input, 0 input, it will be transmitting a weak low, and for 1 input it would be transmitting a weak high. So L and H, as I have told you, it represents weak low and weak high. Remaining outputs will be unknown, that is X. Similarly, we have the not if 1 and the not if 0 gates. So here also the first input is in and the second input is control. Okay, so not if 1 means when the control signal is 1, it is active. So here for this column you will get the inverted value. It's an inverter here, not gate, so you'll get the inverted value. These two values will be X, and 0 is the inactive value of the control signal, and hence the output will be in high impedance state. So here for X and Z, it will be, we really don't know what is the value of X and Z. So it could be a low or it could be a high. So if it is a active signal, then we would get whatever, if the input is 0, we would get a inverted 1, but which will be low. So that will be, H will be transmitted, and for a 1, it would be transmitting a weak low. Okay, and for remaining values it is unknown. For not if 0, this is active when the control signal is 0. So when the control signal is 0, you will get the inverted values X and X, and when the control signal is 1, which is the inactive value of the control signal, the output will be high impedance. Here the output will be high, weak high and weak low, because in complement of 0 is 1, but the 1 will not be strong because the control signal is unknown. Okay, so it will be a weak high, and for 1 is inverted as 0, so it will be a weak low, and the remaining signals are X. So this is the truth table of the not if 1 and the not if 0 gate. The buff if and the not if gates are different from the buff and not gates in the sense that there is an additional control input to these gates. Okay, the instantiation of buff if gates follows like this. That is, the name of the primitive gate is buff if 1. So note the name of the primitive gate here. It is buff if 1, and remember all the keywords in Verilog are in lowercase, followed by some instance label. I will take it as B1, and here the list of outputs first. So here it is single output out, followed by in, and finally lastly the control input. Okay. Likewise, buff if 0, the name of the primitive gate of buff if 0 is buff if 0. So it is 0, not O. Let me take B0 as the instance label. Again, this is also out, in, and control. In a similar manner, we can instantiate the not if gates. So not if 1, the name of the primitive gate is not if 1, and let me take the instance label as say N1, and out, in, control is the terminal list. Similarly, not if 0, let me take the label as N0, out, in, control. In this video, we have learned the basic gates in a different perspective. In the coming videos, we will write programs using gate level modeling, that is by instantiating these primitive gates. Thank you.